Good morning, everyone. Today is the new year. It's January 7th, 2017. So I guess we better get used to saying that the year is 2017 already. So we've had a little bit of a 2-week break in our science conference. So I wanted to open it up and see whether anybody had any burning issues that they would like to start off the new year with. So I see we have Harry's here. Harry has been quite active in the email threads lately. There's been a number of things being discussed about gravity, charge, relativity, and the like. And I see we have Bill Lucas here as well. Welcome, Bill. And we have Bob here.
There wasn't a message sent out on email that I know of. If I'm looking at the emails, I don't see a message. Plus, when I went to the main page and clicked on the link, it didn't work. So some people are probably not going to make it.
Did the link not work again?
Did you get that?
You mean the link for this meeting?
On the main page, well, first off, there's no email. Okay, and I thought maybe you guys weren't gonna, there was no email announcement that I received.
Oh,
well,
yeah,
I went to the main
this
page.
Is Bob. I got it. I got
events.
email. I got it, Bob DeHillstory. So it's out there. Why it misses some and gets others, I don't know, but I got it.
Maybe it's a different email.
All right, thank you, Bob.
Yeah, I noticed that the email also can sometimes take a long time to get out. So I had it set to go out like a half an hour before the meeting. And
yeah, that's a good point. My name is starts with a D, and Ricker, he needs to change his name, I think, and he'll get up on the front end of the list.
The old classroom name thing, right? Although, Harry,
Franklin, since you invited to discuss something, go ahead.
Yeah, go ahead. I want to know what you want to talk about.
Me?
Yeah.
I was going to suggest talking about the LIGO experiment.
Oh, yes, excellent. There have been a number of.
Topic.
Well, why don't you go ahead and introduce what's been going on with the email thread?
Well, I just had there's been controversy about this for several months since they announced it, the discovery of gravity waves. But what got my attention was when I was watching, I think it was Charlie Rose, and he was interviewing somebody on there who I had no idea who it was. And he was going on and on about this was the greatest scientific discovery of the year. I think that's what they were talking about. And about how it was just this really, really super important thing, and really making a big hype. And I thought, well, I think this is kind of old news. But I think the establishment news media is really flogging this, and despite the fact that there's a lot of skepticism out there. So it looks like they've ignored the skepticism, which there's quite a lot of, and just sort of continued the propaganda campaign. So that's really kind of what, when I commented on this, that's sort of what started the recent discussion.
Well, what do you see as the biggest criticisms of LIGO? I mean, what's its biggest problems that you feel that doesn't make it legitimate?
I'm not saying whether it's legitimate or not. I just, I don't know. I did a little research on this, and what I found was there've been claimed gravitational wave discoveries going back to the 1970s, and so to me, it's kind of curious why I can go and get scientific journals and see that they've announced that they've discovered gravitational waves in journals that are 30 years old, and then suddenly now they're telling us that they discovered it. So I don't really understand why they didn't accept the previous announcements of discovery and why this particular discovery is different from the ones that apparently weren't discoveries that were claimed to have been previously. Do you understand my point?
Well, I think part of the point of the email discussion is that this is a great way to make money. Apparently, the number of prizes that the legal investigators have gotten is something in the neighborhood of $7 million. Uh, so it's apparently very profitable, whatever it is.
Well, yeah, there's a lot at stake. There's a lot of money that's been spent. My comment is I have no idea what it is that they claim to have discovered. And my main point is why, I got a book upstairs that says, they've detected gravitational waves. Okay. And apparently this is not new. Detecting gravitational waves apparently isn't new. There's nothing new in that. So what I don't understand is what have they done that supposedly is new that is more convincing than the supposed, I would assume, unconvincing results that were reported in the past. Do you understand what I'm saying?
Well, I'm not familiar with the previous claims that gravity waves have been detected. I mean, can you tell us more about that? Because I've never heard of that we've done that.
Well, Weber, if you go back and look in the astronomy books, Weber, who was at the University of Maryland, they have a lot of the old books. They have this picture of this cylinder that he had, and he put stress sensors on the cylinder and monitored the cylinder, and the thesis being that a gravity wave passing through the cylinder would cause it to move and therefore produce signals on the stress sensors. And that was called a gravity wave antenna or sensor or whatever. And that was in the 60s and 70s. And I'm assuming that he claimed he detected something, but everybody said, oh, no, that's not. And so then they started there's the picture right there. And then they started placing these sensors on two different laboratories, some distance apart, and measuring coincidences. So in other words, I would assume that he measured some kind of an event, and people say, well, that could have been an earthquake or an earth tremor. I don't know enough about this literature to know, but the report that I have is that they use more than one sensor and a link between them so they could measure when the events were coincident at the two different places. And so they supposedly reported events in the book that I have. They're reporting events, and that even shows a graph. I think I forget what report that's in. And I looked at that and I thought, well, this is kind of interesting. But why are they claiming to have discovered gravitational waves now in 2016 when this book that I have claims that they detected it, 40 years ago? So that's about all I can say. To me, this is kind of puzzling. Why these claims appear and why they haven't been accepted.
The article being scrolled had a title saying Weber failed the detection. The title said it failed.
Yes, I'm scrolling through this.
I don't know. All I know is that they've been working on this for years and years, and I don't really know enough about it. That's really my point. I mean, it's sort of like we're supposed to.
One of the questions I would ask is why, on what basis do they predict gravitational waves? And I really am not one to speak because I haven't studied it, but I seem to have thought I read at one time that binary stars moving around each other push on the fabric of space-time and creates a wave in space-time. And that's what they're trying to detect. Now, that's what I remember, but boy, could I be wrong. Because I read it once and
Well, okay. It's not clear to me what they claim they did. All right. They claim to have detected a merging of two black holes. Okay, which is basically what you just said about binary stars. So instead of being binary stars apparently don't generate enough gravity waves and don't merge fast enough. So what they do is they said, okay, two black holes. So we have two black holes that are spiraling into each other, okay, a binary system, and they spiral into each other. And as they radiate energy away, okay, that creates gravity waves, which are supposed to be detected by this device. Okay, the problem is that black holes are pretty speculative to begin with. I mean, you know, I don't believe in them. And if you read Stephen Crothers' analysis of black holes, it's pretty damning what he says. I mean, he says the mathematics doesn't work because what they do is they kind of fudge the fact that they make a lot of simplifying assumptions to get the math to work, and it's kind of suspicious, the whole argument that he gives. Basically, he shows all the flaws in the argument, and when you see all the flaws, you begin to think, you know, hey, this doesn't make a whole lot of sense. And then if you go to my paper, I have a paper or an article on my page at the NP at the JC at the website, JCNPS website, where I talk about black holes. And there's been a lot of controversy about black holes. And, you know, it's like, okay, so we detected something that people aren't really convinced actually exists. You know, so to me, it's all kind of, you know, we detected merging of black holes when black holes are a theoretical object that people basically disagree about whether it really exists or not. So to me, it's all kind of hocus pocus.
I think you're
So
getting,
Are we getting any more people coming into the meeting?
well, I'd have to check. I have to stop sharing and see how many people are here.
I only show 3 people.
I've got 9 showing on my list.
Okay, so I
So
guess
we've
the
got
word
some
is getting
people.
out.
Yep, and it's just the new year, so so I was sharing that article on Weber, and what that says is that, you know, Weber thought his initial experiments showed that, yeah, I found gravitational waves. He built several detectors, and they seem to come in simultaneously. But then other people tried to reproduce his experiments, and they couldn't. So it was a matter that his results couldn't be replicated, and when they looked at Weber's data, that I think they decided that because no one else could replicate his results, that that he couldn't adequately distinguish random events from real signals. So I guess that's why they seem to indicate that it quote unquote failed. It seems, at least that's what this article seems to be saying. So this is just a matter, this is a good thing in science, that once someone comes up with an experiment and publishes a result, that other scientists try and do the same thing. Now, I think that my main objection to LIGO is that that can't happen, because building one of these LIGO inferirometers costs, millions and millions of dollars, and no one else is going to do it. I mean, if I claimed to have an experiment that turned like lead into gold, and I was the only one who did it, I don't think anyone would take me seriously. So the question is, we've got this one LIGO experiment from these one set of experimenters. They make this one claim that they detected black holes, which is it's a huge claim. That's like turning lead into gold. And why should we believe them? Because there's no one else who can independently corroborate what they're doing. At least with Weber's case, you saw his experimental setup. That's something that an experimental group could reasonably set up. But no one's going to set up a 4-kilometer vacuum tube interferometer, at least 2 of them, in order to corroborate this result, right? That would be one of my biggest objections to this, and that it's not independently verified by anybody else.
Franklin Duncan Shaw, one question that has been bothering me about what I've read about the gravity waves is why it has its title, Gravity Waves. Is it a result of a gravitational calamity, the collision of 2 black holes, if they exist? Or is it a wave of a nature that's supposed to cause gravity? Why the name? It's a great name, Gravity Waves, if someone wants to raise money, but what's it mean? Have you or anyone else any idea?
Well, the way I feel about that is that suppose you had a gigantic lead ball, a huge lead ball, maybe 2 or 3 yards in diameter. So that thing generates gravity. And then you stick it on a rail car so you can move it back and forth. Now, what I see a gravity wave is that if you're taking this big ball and you're waving it back and forth, as it gets closer to you, it presents stronger gravity. And when you pull it away, it presents weaker gravity. So a gravity wave is kind of like if you just have this ball oscillating back and forth, you're going to feel this increasing and decreasing gravity. And so that is a kind of a wave, right? And so at least that's how I think they're thinking about it. I mean, for this particular black hole detection, they're basically talking about 2 gigantic like lead balls rotating around each other so that they see this sinusoidal signal of basically stronger gravity and weaker gravity. Does that make sense?
Well, it's an idea, and I certainly don't reject it. I'm wondering if anyone else has any other ideas as to why it's called a gravity wave.
This is Bill Lucas. Can you hear me?
Yeah, we can hear you, Bill.
There's a lot going on here that you need to see the background before you can interpret this experiment. By the way, when I was at University of Maryland this summer, they had a big, thousands of people coming and having meals and presentations and everything on Weber's work at University of Maryland, including Nobel Prize winners and all kinds of people who were there. And but anyway, we're in the postmodern, and in the postmodern philosophy of science, there are people who are considered the experts in each area of science, and each area becomes a separate silo. And they control what is allowed to be published, what are the officially accepted theories. And so it turns out that there's a lot of interest in keeping Einstein's work officially accepted. And so there's been a lot of people doing experiments and finding alternate explanations for dark energy and dark matter and black holes and stuff like that. And so they needed something to officially accepted theory. And so this LIGO experiment was one of those things. And as was pointed out earlier in our conversation, independent researchers can't falsify or discredit this LIGO experiment because they can't afford to do that. It's too much money for an individual researcher to be able to do that. Someone like Donald Trump maybe could afford it, but most of us couldn't do it. And so this is the way they silence the dissidents, the alternate scientists, etc., is by doing this type of event. And you've got to see that, and to see that they also have the money, the government money. So that's what I saw at University of Maryland this summer. They had the big event with Weber, and that's what seems to be going on. And you need to understand what kind of things are people doing that makes them so nervous that they've got to do. And and there is a lot going on out there. And so I'm one of the
Okay.
that participate in that.
Hey, Franklin, leave that screen up right there like that.
Mm-hmm. Yep.
If there's a gravity wave, it has a frequency. And if you look right in the middle at the right end, is this? They have a detectors at 35 hertz to 350 hertz, which are supposed to detect this wave. Now, whether it's a star or a black hole, these are very large objects, and the movement of those large objects uh, is very small, very slow, if anything at all. Most things will motor around them much faster, while these things almost sits virtually still. So I have a problem with the fact that the black hole, excuse me, is moving fast enough to create a 35 hertz wave. I don't get it. Just
Yeah, that's this objection I'm showing. So I'm showing the main article that we initially got about LIGO as a fake. And so this first point, 2.1, is saying that LIGO is not a generic gravitational wave detector. And it's like John Joseph Weber, perhaps created a more generic gravitational wave detector.
But the wavelength is huge to detect
yes.
peak to peak. The frequency is almost non-existent. It'd almost be a straight line instead of a wave. But I can't imagine that those large objects could do that. I'm sorry to interrupt you, but I made my point. I can't believe it's the wavelength of that has to be huge. Yeah, light years. No, yeah, light years long. Excuse me.
Well, that would go to the second objection here, which is that if two black holes were colliding, that particular action would probably take several hours to occur. And like you said, the initial parts of that collision would not happen at 35 hertz, right? In order to get a 35 hertz signal, you'd have to have those things circling around each other at least 35 times per second, right? So you got two black holes orbiting around each other at 35 times per second, which would happen at some point, but you would think that they would have some signal longer than the event, which was, they then mentioned the event time here is 0.15 seconds. I mean, the entire thing was over in like a fraction of a second, right? They didn't see anything before that tiny little time period. So LIGO seems to be specifically geared towards detecting these spinning black hole collisions. So the question is this one of these things where if you're so sensitive to looking for this one event that, if you'll just look at like looking in clouds, if you wait long enough, you'll see anything, right? So if you build this detector, which is doing nothing but looking for this particular black hole collision event, I mean, if enough noise comes in, will you see the event? I mean, that was the same objection with Weber, that he couldn't distinguish noise from actual signal.
But they inject fake signals into the system for testing purposes, and they don't tell anybody whether they're really fake or not until way later.
Yeah, that was one of the incredible stories I heard about LIGO, which is that they did, in fact, inject a fake signal, and they let everyone get excited and almost publish a paper until they said, oh, that was just a test. Which, because they can do that, that kind of like brings into question the entire actual detection, because if someone can deliberately inject a signal into the system like that, not have anybody know, how do we know that they didn't already do that for this detection? Because they run out of money, they needed to show something. Are they beyond the fraudulent data injection?
Have there been any others since that?
Well, Franklin,
Yes. Go ahead, Harry.
Any other detections?
I'm sorry, this is Harry Ricker. That's an issue that's bothered me, which is how do you calibrate a detector to detect something that's never been detected before?
Yeah, that's the problem. Like I said,
normally
if
what you do in engineering is you have a test.
You would think that once they've got it tuned, they'd start showing up all over the place.
Well, they have. They actually have had 2 or 3 additional detections.
With multiple sites. Confirming.
Well, I talked about that earlier, which is they've been claimed detections for 40, 50 years.
Yeah, but the problem I think with Weber's earlier work was other sites did not collaborate at the time he did.
Are they all this same kind of black hole simulation?
Well, the black hole simulation.
No, that's a new thing.
Well, I meant all the detectors that they've reported been these some kind of events that are presumably some kind of black hole self-annihilation or something.
Well, I believe they are, because the LIGO, that's actually the only thing it can detect. The black hole collision is actually the only kind of.
Would you like for me to explain how this works?
Go ahead.
Would you like for me to explain it?
Go ahead.
They use what's called a match filter. They use what's called a match filter, which is an invention that comes out of electrical engineering. What a match filter does is it is a selection or filtering device, okay, that is designed to respond only to the expected waveform. So if I send you a signal and I know what that signal looks like, and you know what that signal looks like, okay, you design a match filter to receive only that signal, okay? And so therefore, you can detect the signal when the noise levels are very high. But you have to know what the signal is that I'm transmitting in order for you to receive it. That's the problem.
That's where the modeling comes in. And so people,
correct,
different theories will model what you will see when you have black holes interacting. And that may or may not be true.
Correct.
Yeah, and so, but
exactly.
So what you do, confirm the model and you confirm the detection of black holes interacting all at the same time together.
Correct. So how do you calibrate this device since you don't know whether your model for detecting black holes is correct? Okay, and so it's based on designing this match filter based on you think you know what the signal looks like. You don't know exactly what the signal looks like. You think you know what the signal looks like. That's what they're doing. Does that make sense to everybody?
Well, they can apply different filters.
Sure.
Right? They can take the raw data and apply different filters, right?
Yes, if you
I don't really know about how they're implementing it. They probably do have different filters.
They do it as a correlator, correlating the received signal with the locally stored signal.
That's what a match filter is. That's a
Calibrate
different
filter
name
with
for a
impulse
match
response
filter.
with time reversal of the ideal one. Yeah, everything tells that that might be that they just inserted that model impulse into the into the system. You know, intentionally or to fake it, or just as a part of routine of.
Right. So to calibrate the system, presumably what you would do is you would generate a signal, okay, electronic signal that basically is generated by your model, okay, and then you see whether that's basically you transmit a signal to the device and look to see whether the device responds correctly to the signal that you've injected, which is your test signal.
Yeah.
But the problem I have is that makes some assumptions about how the device reacts to the actual gravity wave itself.
Don't forget,
I'm just
it's two different locations supposedly syncing up.
Okay, they can send that signal in all the whole system, so that all the stations could receive the same signal. I mean, if they had injected it to the system.
Well, yeah, but they also have to do it in with the proper delay, so it looks like there's some kind of thing propagating at the speed of light.
You know, I mean,
Well,
guys,
in my
if
mind,
one
it's
looks into the genesis of the theory or prediction of gravitational waves, then one can see that everything doesn't have any credibility. You know, everything started with Einstein and that guy Podolsky, right? To publish a paper. First, Einstein was telling that it's not possible to have the gravitational waves. And then Podolsky came, actually, I don't know. Later, actually, that Rosen guy got his position to influence Einstein, to change the mind. So it's still possible to have gravitational waves if one accepts kind of singularities there, and change the coordinate system and things like that, right? And then they rewrote the paper and then published it, right? And at the same time, the Podolsky guy had returned to Russia and had published a paper confirming still that there would not be a way to have such waves, So if one looks into this, kind of really one just, should not care much about that, One cannot be receptive of or accepting the kind of confirmation of those waves whose prediction and postulation or whatever is so questionable,
Well, I would suggest that if you haven't, to read the paper that Stephen Crothers has written about this,
Yeah.
and he sent out an email in response basically to my comment, and he also sent out a video where he confronts the experimenter. And I would, I've read Stephen's papers before. He talks about why basically there's some, how should I put this? You really should read what Stephen says. He's also put out a number of videos. The Electric Universe people, he gave a talk at the Electric Universe symposium a year or two ago, and he gives a pretty good talk about his objections to black holes. And he also talks about his objections to gravity waves. And I can't really say that I understand it because I'm not that familiar with the mathematics that he's talking about, which is general relativity. But his objections and his reasons for saying that it just doesn't work is that they're using a lot of approximations. What in the gravity wave case, They're using what's called the weak field approximation, and he criticizes the mathematical methods that they're using. And he also, the black hole one is a bit more serious in that the black hole is a mathematical solution to the field equations of general relativity, but that solution doesn't permit any other objects to exist in the universe. So the solution is so idealized that it's not really a solution that can be
Actually,
taken
that very
seriously
solution,
as a real
yeah.
physical solution.
Actually, that very solution
Excuse me?
implies that the square of the positive value has negative value. You know. Do you know that?
Well, I just would say
If you look in the equation formula, you will see that that to have the black hole, you have to accept the square of positive number can be negative, is negative.
Yeah, right. All of relativity is based on this kind of mathematics that allow, it's, I don't know. I don't have, I really feel uncomfortable when I see their mathematics of space-time, which is time is on the imaginary axis. What the heck?
I'm scrolling through Stephen Crothers' paper. This is quite a large paper.
He's put out quite a number of papers, and I also recommend looking at the videos.
I still haven't gotten to the basis of his objections to LIGO here.
Well, it's right there. A black hole is a universe. There it is right there. 4. Black hole is a universe. It's right there on the screen. Essentially, what he's saying is that if you have a black hole, that's all that can exist. Nothing else can exist other than that black hole. That's it. So all they can do is say, if a black hole exists, then nothing else exists but that black hole. So then what they do is they try to say, oh, okay, we can put other gravitating masses into this universe. Well, it doesn't exactly, mathematics doesn't really allow that. That's what he's saying. So he's saying, in effect, basically, there are no solutions in general relativity for a universe with 2 black holes in it. There's no solution to that problem. And but what they do is they say, oh, okay, we can make some solutions through approximations. And he objects to that procedure. At least that's my understanding of it. Do you understand what I just said there, Franklin? Does anybody understand what I said?
Somewhat.
Yes, I did.
Well, go back to the 4 where he says a black hole is a universe. That's basically what he's saying is if a black hole exists, that's the only thing that can exist. You understand that?
Yeah.
Let's see here. Where is that? Looking for the word universe. I mean, is this what you're talking about? It says all black hole universes, and then the 5 things here. But yeah, so this is a big paper. So this is Induxera.
Point 3. They contain only one mass. Only one mass. So a black hole, if it exists in the universe, can contain only one mass. So you can't have a universe if it has black holes, because black holes can only exist if there is only one mass object in it. And we know that's false because we know there are multiple objects that have mass.
Well, it is a matter that that's either true or Stephen Crothers has his model wrong. So it's not, I guess, terribly convincing
no, it's not.
on that
That's not
basis.
Stephen. No, stop. That's not what Stephen Crothers says. Stephen Crothers is saying what the mainstream model says. Okay.
No, I don't think
You
the
understand
mainstream
that?
would say that there's that any of this is true. I don't think.
No. Let me go over it again. The solution to the black hole of general relativity that exists, okay, is what he's talking about. Okay. He's not talking about a theory that he made up. He's talking about what the math solutions are for the theory. Okay.
But we know that mainstream
What
already
the
ignores
mainstream
those
does,
when they ignore those at their convenience.
correct. That's what he's saying. He's saying, oh, and on top of that, let's go down here to the point where point four, go to point 4. Okay, black hole universes are not expanding. So if a black hole exists, it can only exist in a universe that isn't expanding, which contradicts what mainstream says, which is that the universe is expanding. So black holes can't exist in an expanding universe. You understand this?
Well, I would still say if you showed this to a mainstream person, they would probably just disagree with all of that. See, they would. I mean, just
Well,
as
of
a
course,
devil's
because if
advocate, they
hold
would
on,
discount
Franklin,
him.
hold on.
Yeah.
Their theory is worth nothing unless they can throw in some ad hoc hypotheses. Okay, so we need more ad hoc stuff to throw into the mathematics so to make it work, because it doesn't work if we do the solutions the way the mathematics says we're supposed to do it. Do you understand this now?
Yeah, well, they just make up something. I mean, they take their pretend black holes and they pretend.
Wait, hold on. That's called an ad hoc hypothesis.
That's right.
Making up something is called an ad hoc hypothesis.
So, I mean, what we have here is not a detector of black holes, but a detector of their ad hoc hypothesis is what we actually have here. So they found, they made up something, they made up something, and they're looking for this specific signal, which is not a very hard signal to reproduce. It's just like a ringing bell. A ringing bell will reproduce the signal. and then they go looking for that thing, and lo and behold, they find it.
Correct. That's what they did.
A dark matter.
Now the real question is,
they for dark matter and dark energy, they had a problem with relativity theory, so they invented that to get rid of the problem.
that's called an ad hoc hypothesis, Bill.
That's right. So I'm saying that's the technique they're using over and over again in this field.
Correct. So dark matter is an ad hoc hypothesis. That's what it is. Dark energy, ad hoc hypothesis.
And you know, the dark matter, at least, is postulated. You know, one should know, really, kind of, at least should think about that. That actually, dark matter has been postulated due to the incorrect Newton theory of orbital motion. You know,
well,
for gravitation, the mass, as you know, it doesn't have any impact. You know, and when you set up differential equation, even with Newton's central force, the mass appears on both sides and gets cancelled. So there is no any impact of mass in terms of how it has been defined. I mean, through F equal m times a or m times g. You know, so I mean, if I look into it closer, I mean, you can just realize that this cause of Newton's wrong theory, Newtonian theory, I mean, of gravitation, or whatever theory where mass has central role.
Well, it's a little more complicated in that what is really happening is that according to the gravitational theories, the orbits of stars in the outer regions of spiral galaxies, they're orbiting faster than they're supposed to, according to the gravitational theory.
So that
And
means
so
it
the
doesn't
ad hoc
obey Newton's
hypothesis-
dynamics.
Well, I think it works both. I don't think general relativity solves that problem either. But I don't think the fields are strong enough that general relativity comes into play.
Definitely not. That's the one that weak points of general relativity that cannot deal with that topic at all.
I'm not sure I understand what you're saying.
I mean, the general relativity cannot deal with that topic. There are some methods, I don't know, to overcome the problem with general relativity, to at all be able to how say, include that problem, to tackle that problem. But you know, it's very, very simple. You know, if you take, I mean, excuse me, can you imagine that you would be able somehow to set up differential equations for dynamics of motion of the Earth around the Sun, without relying on energy conservation and the angular momentum conservation? In that case, you would have mass appearing on both sides of your equations. And that mass would be cancelled. How say? You divide by m on both sides. So, but you know, the problem is that there has been only one force, centripetal force, considered. If you consider centrifugal force as well, explicit centrifugal force, like Leibniz suggested, and even Newton was considering in terms of the apsidal or precession of perihelion of Mercury and so on and so on. You would be able to set up differential equation where mass appears on both sides. And based on that, you will see that mass doesn't enter the how say, calculation. I mean, I have come up with kind of a thermal-gravitational approach, you know. You see actually that you have gravitational constant and you have thermal constant. Really kind of, that the mass, I mean, the biggest problem in physics is the central role of the mass. In spite of the fact that the bodies of different weights or different mass are accelerated same towards the Earth, you know. So this kind of really, really strange thing, you know. So all guys, now I see that all of you guys here in the group are actually, how say, fine with such role of mass. Looking into the kind of variable mass, or I don't know, even negative mass, and so on. On the other hand, actually, the mass is totally irrelevant. Should be relevant, but by centrality of mass, we still are sticking to Aristotle's wrong, how say, doctrine of falling bodies, right? And Galilei kind of finally resolved that, but Newton got it mass back into the game, you know. And since then, mass is already there, all the time there. That's a big mistake. And because of that, mass has to be postulated, otherwise one should have said, oh, that might be so that Newton's theory is wrong. And nobody did say that. That's why we have the dark mass and giving out that big money, you know, to find it, to detect it. No way. Okay, sir.
I think you have the same problem with electric charge, which is that it's just something that has to exist in order to make the theory work.
Great. Yes. Yes. That was my first topic. After I realized this, I said, okay, then Coulomb force again. It's kind of just empirical law, has constant of proportionality. Oh, that might be the same thing, so it might be wrong as well. And then later, of course, I saw that many people were able to kind of elaborate. Nobody actually attacked that very topic aspect, And I would say, okay, let's say if anybody was considering to compare the acceleration of two charges of different size towards certain charge, would that acceleration would be dependent on the charge, or not? I guess not. Same as the mass, different masses are accelerated the same way.
Well, let's talk about mass and charge. So who is that who's speaking on the phone?
Slobodan Edic.
So actually, the emails we've been going back and forth about things like what mass and charge are. So let's talk about that. I know Bill has some ideas about what mass is. Does someone want to tell me what mass is? Slobodan wants to know.
I think we've been talking about this for a couple of years.
Yeah, but it would be important to look into the role of the mass. Okay, let's look into the law of gravitation of Newton. The F equal G m sub 1, m sub 2, or uppercase m, lowercase m, over r squared, right? When you see that expression, and then in the next sentence in the textbooks, you see that actually the masses of different sizes are accelerated the same way. You can say, okay, how come? This is kind of contradictory. It was to me all the time, for 6 occasions, or maybe in my life, and then the people will come up, okay, we use the Newton's second law and say F equal m times a. And then larger mass requires larger force to get a particular amount of acceleration. And then by that, one is able to explain why different masses are accelerated the same way. But if you look now, if you turn around the situation and look how Earth is being attracted by those two bodies, one and then next the other one, then the very formula and then the second Newton law will not work, will not support that. So definitely, Newton's formula for gravitation has been circularly derived and wrong. By that account, Coulomb law would be wrong, at least misleading, I kind of explained, provided that in my paper in Maryland this summer, the end of July. So kind of, I thought it would be kind of really acting as kind of really kind of something new and something worth looking at. But I guess maybe only based on such interaction of this kind of interaction, people might get, provoked and kind of to look into it.
Franklin Duncan Shaw, just to
Slobodan,
bring in a different aspect of gravity, another way of, not of gravity, but of mass. I'm glad the subject is raised because I think it's a good one. But let me run something by you, which is as simple as hell, that mass is a combination of real stuff, something that exists, and energy that it contains, probably by way of vibrations. Period. End of subject. That's just an idea, but I'd like to float it by to see whether there are any reactions to it.
Well, I think one of the reactions that's been going on in emails is that there's this idea that that matter either has something we could call solid, or it's not. I mean, I'm in a discussion with Roger Ryden about, what happens when a positron and electron get together. And, my claim is that I think those things are solid. And, his main question is what prevents those two things from merging into each other? And I say nothing, except that they're like two little marbles, and then they just stop because they are solid, they have surfaces. But, that's my point of view. Other people feel that matter is actually some kind of, say, conglomeration of the ether, or energy. It's like a ball of energy. And that if you looked at matter, then, some people believe that it's, not really anything, right?
It's just either how say ether that has undergone a large pressure, more pressure, and dynamically it got squeezed into smaller areas. Had dynamics where the fluid moves faster and things like that. Kind of, I mean, like an Earth would be something like really kind of as a conglomerate of ether. It's only so that actually we see and perceive the Earth as matter. Like really kind of can see it, can touch it, and so. But the parts of that conglomerate or the condensate is all around, and by that actually, by virtue of that, we can think that maybe Earth and the Sun are attracting to each other, electrostatically, magnetostatically repelling, and things like that. So it's kind of it takes some time, maybe. I find my situation pretty difficult because I somehow came to this kind of insights to came across the work of Dr. Tchaikovsky from Russia. Somehow I'm all the time looking and maybe hoping that I will be able to come up with some translation of the book itself, and then share with you guys, somehow for you to by yourself get into that realm of ether as kind of substrates, gaseous substrates with features featuring the compressibility and viscosity. It's something pretty new in terms of kind of ether conceptualization. Except Tate, long time ago, at the time of Maxwell, later Tesla, and recently those Russian fluid dynamics. In particular, this guy, maybe some German as well, maybe in US there are some, all the time ether has been considered as an ideal of liquid, as ideal fluid, without compressibility and without viscosity.
It's
By having such insight, this guy came up with really totally consistent thermodynamics, including the electromagnetism based on that. With all the stuff, totally, amended Maxwell equations with divergences, non-zero divergences in ether for both electric induction D and magnetic induction B, and so on. That can be translated to A, to the electromagnetic potential, and so on.
Well, how about somebody else? Somebody else here. And the question is matter solid, or is it some condensation of some energy? Does anybody want to represent the idea that mass is some kind of condensation? I see Cornelius has raised his flag, although you're muted.
Is that okay now?
You're okay now.
Okay. Is this coming through clear? Because I've listened to the last couple conferences and people just couldn't hear me.
We can hear you now.
Okay. Well, I'm one of those people that believe that matter is a condensation of energy, and that the ether is a solid tensor field, and so it's all tension between the entire ether is one big massive tension field, And so all the particles and that are nothing more than focused energy or focused waves within that energy field. And so that's where I distinguish what mass is. Mass is basically the inertia or the time delay it takes for those waves to transverse through the tension field. So you have the tension, and then if you have tension in one area, it takes time for that tension to move to the other area. A tension field can support both transverse and longitudinal waves,
Yeah.
and gravity would be a longitudinal wave, and gravity and mass are identical. Basically, it's the same thing. It's just that mass is a focused gravity. So it takes time for gravity waves to move. If you focus those waves to a point, it takes time for that focused spherical pattern to move through a tension field. And it's the tension, and once you get that spherical wave, once you get a wave moving, waves continue to move. Consequently, if you get a pattern of waves that's focused about a point to move, it will continue to move, which is inertia. This is a property of mass and matter. This is how we distinguish what mass is. Mass is essentially an inertially moving point of focused energy. And that energy
So how do
is
you
all,
see an electron? So if you could describe what an
I'll
electron
tell you,
is in your model, how do you describe that?
okay, first off, an electron, and I've said that multiple times, is one of the more sophisticated patterns in this field. The neutron would be the simplest pattern in this field. And a neutron is going to be where you want to start at and understand that first before you understand an electron. Because the neutron essentially has the mass and has a gravitational field associated with it. As a matter of fact, they're one and the same. A neutron is a focused gravitational field. And if you take spherical waves, if you to visualize it, you drop a pebble into a pond and you see circular waves. If you take those circular waves and you put them into a tensionable solid, then you get spherical waves. And it's not that matter creates gravity, its focused gravity becomes matter. So it's totally the reverse of what you think. If you take a tensionable field, and if you were to take an elastic diaphragm and you were to stretch that diaphragm, you would see that as you're stretching it, the tension will automatically focus towards the center of that sheet. And as that tension gets stronger, the tension field, which is the elasticity of the sheet of the media, becomes weaker. As the tension becomes weaker, waves will move slower through it. Consequently, if you were to take that field of tension and vibrate it, or if you were to imagine a rubber sheet or an elastic sheet being vibrated from the edges, those vibrations, due to the fact that the tension will focus towards the center because it's being pulled from all directions, it will automatically focus because the stronger you pull it, the harder you tension it, the weaker it becomes eventually. It has a tension curve. Everything we know of that has elasticity has a tension curve. The tension gets stronger and stronger. It pulls back harder and harder as you pull on a rubber band. For instance, if you pull harder and harder on a rubber band, the tension becomes stronger and stronger. But it will eventually reach to a point where the media will begin to weaken and the tension will get weaker because it's getting towards its point of breaking, the shear strength. So if the field is nothing more than a tension field, and it's not a tension between parts or anything, it's just the tension period, then that wave, any wave you create in that, will move slower towards the area of highest tension because that's where the field is starting to almost break. It's starting, and it's weakening. And if you think about it,
What does that have to do with a neutron? I mean, what is your neutron in the? I mean, I understand
okay,
everything you're saying about like a rubber sheet and you're tensioning it, but where's the particle in that?
okay, well, we're focusing this. We're trying to get this energy to focus, because that's what the particle is the focused energy. Okay, so are you following me where this a wave created in this type of a media, in this elastic media, is going to focus to a point? Are you getting that picture yet, or understanding why that happens? If I create a plane wave in this media, then this plane wave is going to move across this media. But if there's an area where this media is stressed more than other areas, that media is becoming weaker there. Is that correct? Is that making sense to anybody?
But
Well,
we would
if,
also have the areas with increased pressure. You are talking only about tension, not about pressure.
Not at all. No, there's nothing. Pressure doesn't exist. Just tension. Okay. We work up to pressure once we create particles. Before there are particles, there's nothing but tension. Okay, you have to create particles first in this.
Can I make a statement?
But
I would just like to know how you take a nut and a bolt and screw two pieces of metal together with energy and tension.
We're not going to go there. I mean, that's totally sidetracking the conversation, isn't it?
No, that's what mass is. I pick up a nut and a bolt.
No. As I just said, you don't have pressure until after you create particles. Before you create particles, all there is tension. Once we create particles, we can get into where one particle will actually reject another and they won't occupy the same space. But we have to create the pattern of energy that represents the characteristics of a particle. And the simplest particle I'm creating here for you in your mind is a neutron. Okay.
What
so
experiment?
You want to jump to the nuts?
Based on experiments. What experiment shows what you're talking about?
Just simply the observation of tension patterns and how they behave.
I mean, for analogy, is it fair for us to think of your theory as like starting with a very large, thin rubber sheet that's under tension? It kind of sounds like that's what you're talking about. Is it fair to say that we can understand it that way?
That's one part of the analogy, one way to see it. I've also explained the visualization of tension readjusting and tension moving through a field as by observing the tension created by the surface tension of water is a model of tension that you can observe. It's a visible tension movement, because if you create distortions in the surface tension of water, those distortions will move away or move towards each other, depending on the type of distortion you create. What you're seeing is the surface tension itself reacting to an imbalance, and you're seeing the distortion that you create moved, and it's moving under the properties, under the characteristics of the tension's desire, tension's normal activity to readjust and try to rebalance and redistribute itself. That's normal for a tension field, is to try to redistribute the tension energies. And it's all about how those tension energies redistribute. And those tension energies, when you realize the characteristics of a tension field, you realize that the tension energies can become focused. And once those tension energies become focused, we see that as a distinctly separate and unique area of this tension field that we can then say there's a lot of tension energy in that one location, and that is a particle. And it's not a static tension, because we have to keep it, if you just tension a field, how do you keep that particle, how do you keep that tension energy focused in there? And that's why it goes beyond just the static tension, but you begin by understanding how static tension works, how static tension in a field will curve towards the area of the weakest field. And if you can you, so let's start there. Again, we have a plane
by the way,
wave.
Cornelius, do you have like a website or something that has your theories on it?
I'm sorry, I have nothing.
You have nothing. Okay, so You heard it
I
here
have
first.
nothing.
Okay.
Well, you've been
Can you
hearing
tell
it
your
for
name?
Cornelis Verhey. And you, Franklin, have been hearing it for 2 years at least, or 3 years. You know,
Yes.
first time I talked to you guys, I was in the cancer ward and recovering from cancer, and I had lots of time to talk. And I explained the entire process of creating a neutron and creating an electron and what gravity was and what charge was, because you have to create all these things. You have to take essentially nothing other than a tension field, and that nothing consists of nothing more than tension, and you can take that tension.
So somehow, I mean, I find this quite kind of acceptable, understandable, but somehow I would approach more from the pressure side, you know.
Well, that's
from
the problem.
The omnipresent pressure, and then
no, the omnipresent, but pressure does
spontaneous
not work.
formation of structures out of that pressure and precessions.
Pressure
and
does
then, you
not
know,
work.
tension becomes part of it. So somehow, at least I could not. I would rather look at both sides, you know, kind of tension and pressure.
Okay, you can look at both sides, and if you look at pressure, you wind up with against the same brick wall that we've wound up against for years. Pressure does not support a transverse wave. A transverse wave
it's supposed if the medium is compressible and viscous, you know, that's big difference compared to the traditional models of ether.
Medium can be compressible and whatever you want. You cannot
viscous. How say? That's viscosity.
If it's got viscosity, it doesn't let anything else move through it.
No.
Okay. So if it's got viscosity, it has to be rigid. Almost, it has to be like totally solid viscosity in order to properly support a transverse wave.
Not necessarily. I mean, I have some information. I had some presentations, and okay, you know, I have a link. Paid, draw attention to people to it. At least I could send one table with the characteristics, parameters of ether, which provide that kind of consistent electrodynamics and the electromagnetism. Based on that, you can see that the pressures, the velocities, the viscosities, and all the topics, and maybe get some idea or compare with your approach and so on.
If you can draw, if you can come up with
so are you guys seeing? I'm showing a video here.
Yes.
I'm showing a video that's I don't know, may be some of interest, which is that they're showing that, you know, waves can be used to create nodes, which actually can contain particles. Is that something like what you're thinking about?
No, I think you've already got a preconceived notion, and you're not going to listen. So I'll just quit wasting my time and quit speaking, and I'll just listen to you guys. Go for it.
Well, just wondering whether this particular experiment, you know, how you can contain something within a field, whether that's relevant.
Unfortunately, I cannot see. I cannot have access.
If you wanted to, you know, all of this is just a distraction from Brian trying to be able to focus. You have to focus on the basics, and you have to work your way up. You're trying to ask me how to create an electron or what an electron is, and you don't even understand what the fundamental thing is that everything in the universe that we call matter has, and that's mass. And you have to understand what mass is, what gravity is. You guys were asking what mass is, what gravity is, and then you jump to an electron, and you assume an electron has charge, and you have no clue how and why an electron has charge, how the charge is created, where it comes from. And it's just,
and what charge is
like you're trying to explain matter, because matter is composed of matter. I mean, you've got electrons that already are made of little particles, and you have no clue what the particles are made of. You're trying to explain that there's tension between the particles, yet that's action at a distance. Unless you explain what's between those particles, you have action at a distance. You say energy, a vibration of energy causes attraction. What's vibrating? No definition. You have to begin with the basics. The basics are what is mass, what is gravity, and what is action or distance caused by. There is no distance. There is just a continuous field in which tension is varied, and the variation of tension is what we see as everything that exists. It's a density of the tension within a field that causes everything to exist.
Hey,
But you,
Franklin,
Cornelius.
Yes, Bob, go ahead. I think you've been waiting to speak. Go ahead,
yes,
Bob.
I have, but I'm way back on mass, which is about 15 minutes ago.
So what
I
do you
only
think
wanted
mass is?
Well, let me tell you what my main point. One simple point that makes it difficult to answer these questions. Because I had to separate the value of mass from the definition of mass. And that doesn't sound right. But when you think about how the value of mass, the kilogram, is defined, they build this object which has a clear specification, and when they're done, they take a Sharpie and they write on 1 kilogram, which is an arbitrary number. It could have been 1 egg instead of 1 kilogram, but it's an arbitrary number giving value to that object, and we give values to all the other objects we have relative to that assigned value. The value of mass is one thing. What mass is physically is something else, because what you have to do is what Cornelius is doing, although I don't agree with him, but what he is trying to do, which is good, is to try take a mechanism that gets you to what mass is, and then based on that concept, define what mass is. But unfortunately, the value of mass that we use today is totally separate from the concept of what mass is in nature. That's my comment.
All right, Harry, did you have a comment you wanted to make?
Well, I just have a question for Cornelius. Do you or do you not believe in an ether? Is that in your theory?
Ether, okay. In the traditional description of ether, most commonly people describe ether as a fluid-like, ideally fluid-like material that is particleized. In that kind of a description, no. In the kind of description that Einstein used, yes. I mean, Einstein finally succumbed to the fact that, okay, there is an ether, but he said it's non-particle, it has no movable parts, and it can't be given the characteristics of ponderable matter. And so basically, you can either say one of two things. You can say space-time is a tension field, or space-time as a tension field is the ether. It's a tension field, and that's it. I can say, yes, there's an ether. The ether exists of a tension field, period. And beyond that, yeah, okay, yes, there's an ether. That's what it is. But the ether is the tension field. Everything that's within that tension field, all forms of energy, all forms of matter, are just geometric, dynamic changes in that tension pattern. The tension patterns can stay focused and become matter. They can radiate. They can radiate as transverse waves through this tension field. They can radiate as longitudinal waves through this tension field. But it is all a variation in the tension of the field. So that's, yes, there is an ether. If you want to call that ether a tension field. If you want to call space nothing more than a tension field, then there's just space-time. Because basically you were warping space, or you're warping the tension field. So yes, there's an ether, but you have to be specific about how the ether is defined. It's non-particulate. So there's no identifiable, distinguishable parts of it. So you can't, that can be moved relative to each other. And the only thing that moves within that ether is the tension. And we can look at things that are tension. You can look at matter as being focused tension patterns, and once we see those focused tension patterns, one tension pattern we identify matter by how it reacts with other matter. If there's no other matter or nothing else around for the matter to react with, then we don't know it's there even. So it's how one area of the field reacts with the other is how we identify that something is uniquely existing there. And I think Harry, you've been around, and I know that you've heard the description used of like just observing bubbles on the surface of the water, and I just described it earlier, just creating a tension pattern on the surface of the water. You can see that the tension is what's doing the motion, what's causing the motion of the bubbles to move towards each other. Or you can see that the tension of the surface tension of the water is what's causing one item that's hydrophobic and one item that's what do they call it? I'm lost. One piece of material that rejects water, and one piece of material that accepts water. And if you float those two things on the surface tension, you'll get a meniscus that's either an upward going meniscus and a downward going meniscus. If you have two items floating on the surface tension, then you get two upward meniscuses that, if they're the same, and those upward meniscuses will attract each other. It's the tension in that field, in that water field, that's attracting each other. There is a very good article on the CNPS website by I don't think it was Matt Williams. I believe. I'm not sure if I got the name right. He just put out, and I believe he actually did some studies on the nuclearization of bubbles, the energy of nucleating bubbles, and that is all about the study of tension and the tension characteristics within a media that has tension. But you have to get rid of them. You have to not look at the media that the tension is in, but look at the tension's behavior. What the media allows us to do is interact with our world and see how tension moves. But if we get down to the very, very, very lowest level, where we get down to the ether is nothing more than a tension field. And once we identify a location in that tension field by giving it a specific pattern of tension, now we have matter. We can look at one piece of tension, one area of tension, one tension pattern, and compare it to another tension pattern in its proximity, and we can see how they react, how they overlap, how they interact, and how one tension pattern will reject another and one tension pattern will accept another. But it still all gets down to, yes, ether is a tension field, and that's it. There's no particular characteristic to it. So long answer, Harry, sorry, but yes, there's ether.
Cornelius, what equations do you use for energy?
I don't use equations at all. My physics is strictly visualization, strictly observation, visualization, and logic. I don't have mathematical skills to create these equations. I would love to be able to create equations telling you this is the size of this bubble and the surface tension of the water, and this is the size of a bubble nearby, and how fast are those two bubbles going to combine? Because if you observe something like that, you observe two different surface tension areas on the surface of water, you'll notice that as the two distortions approach each other, they begin to accelerate towards each other, and mathematics would probably describe that as accelerating towards each other, probably somewhat close to the approximation of two objects moving together in space under gravitational force. Inverse square law says the closer they get, the faster they'll accelerate. Observations show that the tension field in the surface of the water does something similar to that. Again, the tension field in the surface of the water is not gravity. Actually, it actually is, but it's on a subatomic scale. But it allows us to visualize or see that. So it's more about being able to visualize the tension patterns and understand why the tension patterns behave the way they do that I deal with, and not the mathematics. Because my mathematical skills to create an equation for what I just described to you, even is, that's a simple activity, a couple of bubbles moving together, but create an equation describing how fast they're going to move together and why is an entirely different facet of science that I'm not good at. Let's put it that way.
Cornelius
My,
Duncan
my,
Shaw.
my skills lie in visualization and observation.
Cornelius Duncan Shaw, is there any reason why your tension field cannot have ponderable substance?
Because ponderable substance implies that most often that would imply particulate substance. And if there's particulate substance and you say that there's a tension between this particulate substance, you have to define, you have action at a distance, or else you have to redefine what's the tension. It's a never ending, there's no reason for there to be particulate substance because, for one thing, a particulate substance cannot support a transverse wave, which is light, because, unless you have tension between the particles. And like I said, then you're stuck. But a solid can support transverse waves and longitudinal waves both. Anybody that's in seismology that's ever studied seismology, ever explored for oil or whatever underground, realize that the transverse waves do not move through a fluid. That's how you detect that there's a fluid, is the transverse waves stop, the longitudinal waves continue. You cannot find a shear wave that travels through anything but a solid.
Or viscous.
You can make it viscous, and it'll travel through a short ways, but it'll quickly dissipate because it's got viscosity. You can't get light to travel from here to eternity and travel without loss of energy. A transverse wave that travels that far has got to be traveling through nothing more than a solid that's totally tension. Like I said, if a tension field suffices to explain both the propagation of transverse waves and longitudinal waves, why do we need to complicate it by adding an additional particulate layer that we then cannot explain what the tension between the particles is without going back to the next level? Eventually, you're going to get to all there is the tension, and the particles are patterns of tension. Focused particles, particles are focused patterns of tension. We also know that particles do not have a defined edge, and that's because the tension is focused and it gets weaker with distance. And at a certain point, we say, well, 99% of the energy or the strength of the particle is contained in this area, and therefore that's the diameter of the particle. But in reality, the field that is associated with that particle and creates that particle extends forever. And there's a lot more to it than that. And I think, Franklin, I told you, you and Glenn Baxter years ago, that one of the things that you stumbled upon was very important, and you should concentrate on that. And that was the observation that if you observed spherical waves or circular waves, that in the media, tension media, the waves get longer as they get farther away from the focal point. And that's a very, very critical characteristic of how gravity can work. And it's a very, very real thing. If you look at, if the tension is strongest towards the middle, you expect the waves to move slower because the media is weakening. And so if the media is weak towards the middle, the waves are going to move slower, they're going to be more compact. If the media is not weak, is strong out in space, like out in empty space, there's there's not a lot of compact patterns of energy, which is matter. And so the media allows the gravitational waves to move very fast, almost infinitely fast. But when you get down towards the size of an atom, and gravity is nothing, atoms are nothing more than focused patterns of gravity, then the waves get denser and denser and closer together. And so your energy becomes exponentially larger. And you can also, you can also then explain why there's such a difference between the strong and weak nuclear forces and gravity, because gravity is not linear. It becomes stronger and stronger as it gets to, or not stronger and stronger, it becomes denser and denser as it gets towards the focal point of this energy. And it's a whole inverse universe thing if you really look at it. The weakest place and the really most empty place in the entire universe from an ether standpoint is the center of the nucleus of a neutron. Because at that point, you have stressed the media. There's so much tension that the media is at the point of breakage. But when you think about it, once you break a media, the wave can no longer move through it. So consequently, the tension wave cannot move through a media that is totally broken. And at that point, the wave is going to get distorted and no longer be spherical, but it's going to start to wobble because it can't support the energy going straight through it. So the energy is going to go around it, and you're going to create a wobble in that spherical pattern. And the wobble basically creates transverse waves that are going around the spherical pattern on top of the longitudinal waves that are creating the spherical pattern. The transverse waves are now electromagnetics. That's electromagnetics as transfers. And the transverse waves are going around the spherical pattern on each wave, each consecutive longitudinal wave that's making that spherical pattern of waves, which the spherical pattern of waves gets longer the farther you go away from their focal point. Those transverse waves going around the spherical pattern is what gives you electricity. And electricity is, okay, you have the is there anybody following this at all? I'm going on and on here.
I'm getting a little bit lost, but I mean, this is kind of what we do at the CNPS. We explore new ideas. So if you're here to learn about new ideas, and certainly Cornelius, your idea about tension field as being fundamental. I mean, I think that's a new and interesting idea, but I'm not quite sure we're quite following all the details.
Well, I think I better slow down a bit, and maybe I'm probably going on too far here. I all of a sudden got into, we're starting to create an electrical pattern in here, and I think we need to concentrate on mass and gravity and how that reacts to between simply neutral objects. First, we need.
Yeah, well, I think you ask a lot of good questions. So, but since we're talking about mass, let's just try to get back to the topic of what people think mass is. There's been a couple of email threads, so I'm going to show one of them here. Between actually me and Harry, we've been talking about what these concepts are. So I have one email here. So, but there were 3 points that I was trying to make about matter and actually mass. So the first point I have is that being a believer in the solid nature of particles, which is different from your view, Cornelius, is that I believe that particles do have surfaces that they can basically rest on, and that they are basically hard little balls. Now, I don't know why is it that mainstream physics doesn't like this idea that, if you took an electron and if you had a sufficiently powerful microscope, that you would in fact find out that it's a hard little ball. And so that's point one.
Bill Lucas is going to object to that, I can tell.
Oh, yes, he is. But
Bill Lucas is the expert on it.
I would object as well.
Yes, but that's kind of my opinion on it. Yes.
Franklin,
go ahead, Harry.
You have an opinion, okay?
Yes, that's my opinion. It's totally my opinion.
Have you bothered to look at what I wrote about the history of magnetism? It's there at the GSJ. Have you looked at it? Have you taken the time to think about it and read it?
No, I
Okay,
need to go do that. That's
just a
on my to-do
question.
list.
All right, let me just say, okay, what I do there is I kind of explore the history of the concept of magnetism. Now, what happens and what you see is people have been talking about this particle idea since the very beginning. That goes back to Democritus, okay? And the whole idea of what an atom is this fundamental particle, all right? Here we are after how many years of talking about this, and mainstream hasn't really made much of progress on this. They talk about light is a photon, which is what? Some kind of a particle. Problem is, this idea of what a particle is isn't really well defined at all. Okay. What you said is it's a hard ball. Okay. Bill Lucas says that it's a toroidal structure. Some of the people in mainstream say it's a thing called a string, whatever that means. Okay. It seems to me we're not really making any progress on this by saying, I think that the world is made up of these kinds of objects. What we need to do is ask ourselves, what are the facts of experiments? And Bill Lucas seems to be the only person who can tell us that.
If I might make a comment, I'd like to try and connect what Cornelius is saying. And basically, Cornelius says that particles are focused patterns of tension. And when research was
Bill, let me stop you. Let me stop you here, Bill. Particle is an idealized concept. So when Cornelius says a particle is something that is different from what we think a particle is, that's kind of a non sequitur. Do you understand what I'm saying?
Right, but
Harry, I think Bill is right on track. Bill is saying a particle is focused energy, and Bill and I agree about that. What Bill and I don't agree about is the geometries of those focused energies, but I think Bill and I both agree, and probably the characteristics of the media, because Bill's toroidal description, although I believe is somewhat accurate, the toroidal description he gives as a soliton, I believe that takes too much of the characteristics of the fluidic space characteristic and works with this as opposed to a solid tension characteristic. I think I've talked about Bill's before, the polarization characteristics. But anyway, I'll let Bill go back to speaking. But I think Bill is on track with the concept of it being focused energy, and I think that's where he was going. But I'll let you take over again, or finish, Bill.
okay. The experiments that have been done with electromagnetic fields. There's a fellow who did experiments at University of California at Berkeley, and he discovered 13 properties of electric and magnetic fields. And one of those properties is that the field is continuous and has tensile strength. The field is not composed of microscopic items, but it is a continuous thing. And then what Winston Bostic, the last graduate student of Arthur Compton, discovered was that.
Bill, can I stop you here?
Okay.
The key word is discrete and the other word is continuous. Okay. Yeah. What a particle is discrete. So what you're talking about is discreteness. That's what a particle is. It's discrete. And what Cornelius is saying is that it's not discrete. It's a localization in the field that is continuous. Yeah, does that make sense?
My idea of particle is not the same as your idea of particle.
No, I'm not saying that.
Because the work of Winston Bostic showed that it has no dimension. It doesn't have a finite size. It extends a tremendous distance, but it is a standing wave. If you
Right, Bill. I agree with that, Bill. I think Harry misrepresented what I said because I don't feel like it's a localized. I said that before. I said the energy pattern continues infinitely into space. It is 99% of the energy is focused. The density of the energy is very strongly focused at the region of the center of the particle. But the particle is an infinite size, and I think that's exactly what Bostic was saying too, and you're saying also.
My objection to this, Cornelius, is the use of the word particle, okay? Because particle implies discreteness, and your description doesn't imply discreteness to me. Do you understand that?
And I just described what a particle is as a focus.
How about say structures?
You basically have to define. We can throw out the word particle and we can just say focused energy pattern, and we can describe a focused energy pattern that gives us the characteristic of a neutron. We can describe a focused energy pattern that gives us the characteristics of an electron, and we can say these are all focused energy patterns. We can get rid of the photon being a particle, and we can say the photon is a single wavelet like a tsunami wave traveling across the surface of the water, and say that single wave is a photon, and we can say it is part of an entire field, and the energy that's concentrated in that location, we can say that's a particle. I agree with you. The word particle is misleading because everybody believes a particle is a discrete, separate, solid little ball type thing that's totally separate, and yet they say with this particle is associated a gravitational field. Well, in reality, the gravitational field and the particle are one. It's just where the density of that gravitational energy is strongest. We say that's the localized area where it's strongest. We call that a particle. Physics calls that a particle. The word particle is misleading if you look at it as being discrete and separate from the rest of space. There's no such thing as separate from the rest of space.
If we would be talking about structure, with particular characteristics, with particular topology, like movement of say some sub-elemental fluid elements with such velocity, such as density, tangent, whatever, and then creates, for example, the toroidal vortex. We then understand that actually everywhere we have movement. Nothing static, nothing solid.
That's correct.
But based on the characteristics, based on how those features are detected, how they interact between each other, then we can, conditionally talk about maybe not particles in traditional way, but some structures that can be named this way or the other.
Correct. That's correct. We call that particular structure or that particular pattern a neutron, or we call that particular pattern an electron. It's a pattern that we can idealize.
We can say soliton, but on the soliton we have to visualize it. For example, to have in mind that particular shape of the smoker ring, right? So, Bill, when you say toroidal whatever particle or structure, and then talking about soliton or standing wave, do you have in mind something like smoker's ring?
The Winston Bostic, made out of the electromagnetic field standing wave solitons, and they were shaped like a toroidal ring, and but they didn't have a finite size.
Yeah, sure. But what is the inner structure or configuration of such an object? Is it like smoker's ring, wherein small particles of smoke, gas, are running all around and they're creating that shape. Like we have solenoid, for example. Imagine those wires and so on. But imagine that everything is streaming, flowing, And in that flow, through the density, through the velocity, tension as well, I'm not sure that I'm kind of really well distinguishing the pressure and tension and so on. That we can something like topology, but behind it, intrinsically, we still have movements of elements of fluid at certain scale, and then those scales maybe then differ by order, and we have the same mechanism, the same shapes, but just the elements of that substrate of the fluid
I
are
would
changing
disagree
in
with
size.
that concept, but what do you think, Bill?
You're talking about what does the field consist of?
Yeah. What's the inside? Is something static or dynamic? Is something streaming, something moving? And that particular elements, those particular elements, again, maybe having some substructure,
Experiments and the empirical laws of electrodynamics say the field is composed of subparticles.
Bill, could you move a little closer to your mic? I think you're getting weaker.
And so, but it does have different densities and tensions, and it has structures, which I call geometrical structures. But the geometrical structures are not quite like what we would do in geometry because they extend to infinity, but they have certain patterns of symmetry that you can identify. And then from that pattern of symmetry, you can say this pattern is electron, or this pattern is and this pattern is made up, for an atom, is made up of multiple subpatterns that are coming together. But they have one atom is in equilibrium with atoms light years away. They're not separate, completely independent things. They're somewhat dependent on one another. Someone else can talk if they like.
Okay, well, actually, we're getting close to the top of the hour. So I wanted to ask whether anyone else had any other comment before we close.
Franklin, you're saying that what mass is particles that are discrete, that have definitive geometric shapes, and the shape that you prefer is a sphere. And so you say a particle is a sphere and it's solid inside. And as I understand it, you say there's nothing outside of it. Is that correct?
Well, it's consistent with that idea. Although if you ask me specifically what an electron is, I would probably still have to say I don't know.
Okay, well, that's not my point. So your idea of what a particle is that it's an object that exists inside of space that is a discrete object. I think
that is
the
correct.
correct word is discrete, topologically discrete. So it doesn't have any other connection outside of itself. It's a spherical object, has spherical symmetry, has a hard surface, and it is defined by that surface. And it does not have, outside of that, it's discrete topologically. There's empty space outside of it.
Yeah, I would agree with that.
Okay, now that's a different conception from what Cornelius is talking about. He's saying that the particle is a localization of the field that looks like it can be discrete because of the way the intensity of the field changes. Does that make sense, Cornelius, what I just said? That's my understanding of it.
Yeah, that's a correct concept, because you still need to describe the tension or the the action between the discrete particles, if you have discrete particles, but with it being the field, there's always action between one area of the field and the other because the field is continuous. There's no such thing as action at a distance because it's all one piece. So yes, that's correct, Harry.
Then that will correspond to my views and to Bill Lucas' views as well, so they could start working together on it.
Well, we all have
Well,
very
I would
different
argue,
views.
I'm gonna really throw people into a tizzy here, and I'm gonna say that my view is that Aristotle's conception was basically what Cornelius was saying, and I would say that the Democritus conception was more like what Franklin is saying, and those two conceptions have existed since the Greek era, and which one of them is true really hasn't been resolved, I think, by modern science.
Well, I don't know about Aristotle or anything, but I mean, basically with the concept that I've described and that Bill's describing, I think we can actually give you the geometries of the various particles or various energy patterns that we call the neutron, the electron, the photon, the proton. The geometries of those wave patterns or those tension wave patterns is what's just definitely definable and logically derivable.
All right. Well, I think today we have heard a lot of different things. I'm getting a big echo here from somebody.
There's some echo with Franklin.
Let's see here. Did that fix the echo? Okay. No, the echo is still on. And I think I muted everybody. So I don't know where the echo is coming from. Well, I guess I'm still going to have to try and end the meeting with the echo. Oh, wait a minute. Maybe it's from Harry. Okay, is that good? Okay, yeah, we were getting an echo there. So we're at the top of the hour here, so I'm going to try and summarize a little bit here. So today we had started out our discussion about what LIGO is, and so I am sharing right now. There are two links. One is to the LIGO fake blogs. And the second one is to Vixera, which is Stephen Crothers' paper. And let's see here. So we discussed things about like the LIGO is this thing which detects the theoretical merging of black holes, and that basically LIGO is simply designed to as Harry says, it has a filter just specifically designed to recognize that signature. So it's not really a generalized, but we did learn some things also that there have been some other attempts at seeing gravity waves from Joseph Weber, and that his work was somewhat discredited. But so we did learn some things about that. And then our discussion got into the question of, what on earth is mass and charge? And we did hear a lot from Cornelius Viher today about his particular idea that it's based around tension. So that's an interesting new idea. So if you're here for new ideas, well, that's one of them. And that would be opposed to, I mean, the key opposing ideas here are whether particles like electrons or whatnot what are they really made out of? Are they made out of focused energy? Are they some kind of condensation of something else? Or are they truly just little hard balls in empty space? So those are the two really big kind of thoughts on what particles could possibly be. And then if you go to the mainstream, we haven't even discussed the fact that mainstream thinks that particles are waves. And with this whole particle wave duality thing, we didn't even get into that. So, but maybe next week. But I think that will conclude this week's discussion. We can continue this next week. And if you guys have any particular topics you'd like to speak on, please go ahead and email me, franklinh at yahoo.com. And I'll be happy to get the discussion started around those. All right, so thank you all for participating. And I believe these recordings should show up in YouTube later on if you wanted to review anything else. All right, so thanks everyone, and have a good week.